Okay, today I'd like to introduce you to something known as phase velocity, how it applies to electrons and how it can and in certain situations must be greater than the speed of light. And also why that is not a problem. Phase velocity is a characteristic of several combined waves, usually a wave packet. Here we are going to consider the phase velocity of matter waves, specifically the electron. Since electrons have both particle and wave-like properties, a wave packet is an effective example and method to represent its behavior. And a wave packet can look at something like this, where you have an overall wave shape, but you also have these individual wave shapes. A wave packet mathematically can be achieved by a sum of regular sine or cosine waves. A reminder here that the letters I'll be using, K is wave number, and that is wave cycles per unit distance, and W, or omega, is angular frequency, which is just radians per unit time. It should also be mentioned that these values are always positive. K is usually vector more accurately, but here we're just going to use the scalar form. The vector would have the regular K as its magnitude and its direction being the direction of the wave. Yes, for our purposes, we'll stick to the scalar quantity. So let's see if we can take a simple sum of, in our case, cosine equations and get something that more represents a wave packet's behavior. Okay. Now in this form, this doesn't mean a whole lot to us. So what we want to do is take this from a sum to a product. The algebra I'll put on screen here, but it ends up coming to just this. 2 y naught cosine delta k over 2 x minus delta w over 2t, and then times cosine k1 plus k2 over 2 x minus w1 plus w2 over 2 t. Now this and this, that I will just write from here on as k bar and w bar for the average value. And so this here actually turns into cosine k bar x minus w bar t. So, in fact, this is very useful because if we go back to our little wave packet here, this outer wave shape is governed by this first equation. And this inner shape is governed by this equation. And this, we can find the velocity out of this wave equation, which I'll do in a second. And that will give us the group velocity, the velocity of this group, this wave packet. And then this will give us the phase velocity. And as you may be able to see, the velocities here can be different. And I'll show an image on screen here that exemplifies that. Because it is actually quite difficult to visualize sometimes. Now let's try to get velocities out of these. Let's recall this first equation we had over here. Yeah, so we can take this equation and we can do this to it. We can do y naught cosine. Let's draw out the 2 pi. We have x over lambda minus t over t, capital T. It's kind of weird. And then we can take out a factor of 1 over lambda, And this becomes y naught cosine 2 pi over lambda x minus vt. So we're going to apply the same sort of work to these equations, and we're just going to see what this value is. So let's do that. I'll call this equation 1, and I'll call this equation 2. So for 1 half delta k x minus delta w over delta k t, and then extra there. So we see that this is our v value. Remember, this is our group velocity, the big shape. And so we can call our group velocity equal to delta w over delta k. Now for 2, we have k bar x minus w bar over k bar t, which goes to w bar over k bar, because that. So, okay, we have these defined here for our two-wave case. But maybe we want to see something a little more general. Maybe you summed an infinite amount of waves. Now, we'll touch on a second here. The difference between these two velocities, we'll go into a bit more detail later, but the important part to understand is that phase velocity isn't really real. It's not really a physical thing. It doesn't carry information. And so it's not really a problem if it goes faster than the speed of light, because special relativity really only forbids information from traveling faster than the speed of light. Phase velocity is just kind of like the monochromatic virtual wave within this. So let's consider the infinite sum case to further flesh out these definitions into a general description. If we sum up an infinite number of waves, all with infinitesimally different k values, we will get a single perfect wave packet, one-dimensionally in our case. I will simply show what this means for our aforementioned velocities and not go too deep into the math, because the math is quite difficult. So I'm going to erase most of this here. Okay, so let us recall some of our ingredients here that we'll use in this situation. We have lambda over t is also just lambda times f, which is equal to v. More accurately here, this is phase velocity. And then group velocity equaling dw over dk. Notice this is the calculus version now. This is not delta, this is d. Phase velocity is equal to f times lambda, which you can also just see as w over 2 pi, and then 2 pi over k. Those will cancel, and you're left with w over k. So it's just kind of like the general version. Instead of w bar over k bar, it's w over k. Now notice something interesting here. We can rearrange these things into w equals k vp. But wait a minute, we have this definition here. So if we take the derivative of this with respect to k, then we'll get the group velocity in terms of phase velocity. Let's do that. So yeah, differentiating this with respect to k, we get vg equals vp plus, of course, k dvp over dk. So we have this. This is an important term here, because if this term is 0, then phase velocity and group velocity are equal. Specifically, if this term is 0, then this is what is known as a non-dispersive case, or a wave is traveling through a non-dispersive medium. This occurs in waves on a string, on a perfect string, sound waves in air, and later, as we'll see, electromagnetic waves in a vacuum. Since all the waves move at the same speed, the wave packet is not going to change throughout time. Oppositely, there are dispersive cases where this is non-zero. This happens in water waves, imperfect wire, or imperfect string, light in a medium in which the index of refraction is slightly frequency dependent, and for our case, matter waves. In this final example, this final example of matter waves we will examine further to prove how phase velocity may in fact exceed the speed of light. So let's just conceptualize an electron wave and prove that phase velocity can indeed be greater than c. For this, we'll be using the de Broglie relations for wavelength and frequency, the origins of which probably deserve their own video. And we will also use everyone's favorite energy momentum equivalence from special relativity. So all this is above board for Mr. Einstein. Okay. So yeah, you have W equals 2 pi f. You have K equals 2 pi over lambda. I know I'm writing these all out again. I just like to see them. E equals hf. P equals h bar k. A reminder that h bar is just off of h by a factor of 2 pi. Vp is equal to W over k, which equals 2 pi f over k. From this, we can also get that f is equal to E over h. So this can then become 2 pi E over hk. And then, of course, we have the energy momentum equivalence, E squared equals P squared, C squared plus M squared C to the fourth. Also, the origin of E equals MC squared, which pops out if the momentum is 0, the rest mass energy. Okay, so to make this a bit easier in my calculations, I'm going to pull out a factor of c squared, and I'm going to apply a square root to everything. So E will in fact be equal to c times this. Okay, so let's take this, let's plug it in here, and we get Vp is equal to 2 pi c p squared plus m squared c squared square root over h k. But of course we know that since we have a 2 pi up there and h there, we can just put a h bar on the bottom. This p squared I'm going to change to h bar k squared in accordance with this. And then yeah, and now we can do an interesting thing. We can take this h bar k and distribute it under the rational. And so we get that Vp is equal to c times 1 plus m squared c squared over h bar k squared. Obviously, this rational term is strictly greater than 0, and it's multiplied by a factor of c, so it has to be greater than c. So that's pretty cool. Now let's go further and just make sure that everything agrees here. Make sure our theory is consistent. We want to make sure that the group velocity is equal to our particle velocity, just so that we know for sure we can make this link between waves and particles. I'll do it over here. Okay, so first for the particle, we know E equals gamma mc squared. So E over c squared is equal to gamma m. And the P equals gamma mv. So V is P over gamma m. So V equals PC squared over E. And that's what we want to verify from our wave stuff over here. This is the particle velocity. Vg is equal to dw over dk. Recall that w is equal to vp times k. So we already know vp, it's right here. So let's times that by a factor of k and then differentiate with respect to k. So we have w equals c over h bar k squared plus mc squared. Yes, okay, now applying the derivative, we get dw with respect to k is nothing but c over h bar. Obviously for the square root, we'll do 2 times h bar k squared plus c squared, like that. And then we'll multiply it by 2 h bar k times h bar. And so this 2 is going to cancel. This one factor of h bar on the top is going to cancel. And so recognizing that a single factor of h bar and k is going to equal just p. So we have pc on the top. And so we get pc over, I'm turning this back into p, p squared plus m squared c squared on the bottom. But remember, from this equation, p plus m squared c squared is nothing but e over c. So this is just e over c. And so we end up with p c squared over e is the group velocity, which indeed is equal to our particle velocity. But now with these two ideas, let's go a bit deeper. And this is where it starts to get pretty interesting, I think. There's actually a deeper law here between phase velocity and group velocity. Group velocity is dw dk pc squared over e. And E is hf equals 2 pi h bar f equals h bar w p equals h bar k. And so we can put this in terms of de Broglie relations, and we get h bar k c squared over h bar w. And you may remember from algebra class that these cancel. And we get k c squared over w. But wait a minute. This is group velocity. And we said that phase velocity was simply equal to W over K. That's remarkably close. That's only off by a factor of 1 over c squared. So indeed, we can say that this group velocity is pretty much just equal to c squared over the phase velocity. And so rearranging this, we find that phase velocity times group velocity is equal to c squared. I think that's pretty cool. And so this does, in fact, reveal a deeper relationship between phase velocity and group velocity, albeit in our case just for matter waves. Phase velocity obviously must be greater than c here. It literally has to be, because group velocity is just equal to our particle velocity, which of course is mass dependent, and anything with mass can't go faster than the speed of light. So phase velocity has to pick up the slack and be greater than c. In addition, you may recognize that electromagnetic waves in a vacuum also follow this law, since phase velocity and group velocity are both c. Yes, and so finally, let's just finish this all off with verifying this with the equations we found earlier, namely this one and this one.
Vg equals pc squared over E. And Vp is c1 plus m squared c squared over p squared.
And so putting these together, we get pc cubed over E, 1 plus m squared c squared over p squared. And so I'm going to drag a factor of p out here. And so that's going to cancel. So we're just going to be left with c cubed over E is equal to p squared plus m squared c squared. But wait, it's that one again. This is nothing but E over c. C cubed over E times E over c, obviously c squared. There it is. That is why phase velocity of matter waves can and must be greater than the speed of light. Thank you.